Welcome everyone, this video is the third video of a series on this channel where I discuss new stuff that I learned during my undergraduate physics degree. For those of you who don't know me, my name is Arda Kurtoğlu and I am a physics undergraduate student at the University of Oxford. In this video I will be discussing a spectacular mathematical theory called complex analysis. And to do so I will tackle an integral that's called the Dirichlet integral. And I want to let you guys know that this is one of the easiest applications maybe of complex analysis, and even this is fascinating. When I first learned about this topic, I was amazed, truly amazed. And as I'm saying again, this application that we're about to do is only the beginning of things that you can do with complex analysis. So it's incredibly useful, incredibly beautiful, incredibly powerful. So without further ado, let's get into it. Alright everyone, so the integral that we want to find is this integral that you see on the board right now. And as I said, it's called the Dirichlet integral. And I am almost sure that I'm pronouncing the name incorrectly, so I apologize for that in advance. Dirichlet. I hope that's somewhat reasonable. But okay, so we want to evaluate this integral. And obviously, since it's a bounded integral, it has limits, right? The upper and lower limit. The answer is going to be a number, right? And the way we are going to do this, normally when we tackle integrals, we find the we would find the antiderivative of the integrand, and then we would evaluate at the boundaries. But that's not possible for this integrand, sin x over x. You can't really find a closed form solution for this. And in fact, the beauty of complex analysis is, it lets us evaluate crazy integrals without doing any integration. We are not going to be doing an integral to calculate the value of this integral. That's truly amazing. And how will we do this? Well, we first need an insight, which isn't that hard, I hope. If you look at inside here, right? If you look at integrand, you'll notice that sin of x is an odd function, right? We know it's Taylor expansion. We know it's Maclaurin series. It goes like x minus x cubed over 3 factorial, stuff like that, right? So that's odd. Then you divide that by another odd function. At the end, you would have something that's like 1 minus x squared over 3 factorial and goes on and on. So you would have a function that's even. So the integrand here is even, which means that it's the same on the positive and negative sides of the x-axis, right? It doesn't change its value for positive and negative x. So if I call this integral I, which is the thing we're trying to find, we can conclude that if we consider this integral, then this would equal, this would be twice I, right? So in fact, we can rephrase the question as I equaling 1/2, and then the bound is now from minus infinity to infinity. You might say, okay, how is this easier? Well, you will hopefully by the end of this video see why we've made this decision. Okay, and now comes the beauty of complex integration. And I will be using some results without proving them here. If you would like to see the proofs, there are textbooks, there are other videos, or just let me know in the comment section. I can make a separate video where I prove these results. To do complex integration, we would need to choose a contour to work with. Right? So I'm drawing the Argand plane with the real and the imaginary axis. So that's that. And now I want to do a substitution. I will now consider I tilde, which will be a complex integral. It will be e to the power of iz Sorry, the pen is not really working nicely. Sorry about that. iz over z. Let me write with my hand maybe. No. Okay. iz over z over some closed contour, right? Over the contour C. I'm considering this integral out of nowhere. And in fact, if you do some complex analysis, you will realize you need to choose your contours carefully, and that's something you can get into the habit of doing only by practicing, as is the thing with most of the things in life. So out of nowhere, I choose to evaluate this integral. But it's not that out of nowhere, right? Because at the bottom we had x, but now we have z. So that's something. And also, at the top we have e to the power of iz, and you know, like if we take the imaginary part of that, that's sine of x, sine of z. So we sort of see why we would do such a thing. So it isn't completely arbitrary, right? We can sort of see what we're doing here. And what is the contour? Well, I will choose such a contour. So this is the contour. I will do like a semicircle here with radius epsilon, let's say. Radius epsilon. Then I will go on to a radius r here, and this was minus r. Then I will do another semicircle like that. And let's say I'm traversing in this direction. So this is the contour that I call C. Now, the beautiful thing about complex analysis, complex integration, is there is a theorem called Cauchy's integral theorem, or Cauchy's residue theorem, I think, more specifically. And that basically says, unlike this would require a lot of discussions about residues and stuff, as I'm saying, we're doing a simple application to just build some appetite, hopefully, for the topic. So Cauchy's integral theory, or, well, what is it called? Cauchy's residue theorem, I think. It tells you that this integral, right, this sort of contour integral would equal 2 pi I times the sum of the residues. So I'll put like sum of the residues. And I don't really want to discuss what a residue is, but basically if you were to do an expansion for the complex function you're considering, there would be like bunch of terms, and if you're allowing, you would have the polynomials, right? That's the Taylor expansion. And then you would have the other parts, which would be like, I don't know, 1 over z squared maybe. Not 1, let's say a over z squared plus b over z, stuff like that. Then in the expansion, the b here, b, would be the residue. Okay, so it's the coefficient of the 1 over z term. And the thing is, since it has to do with 1 over z, right? You can see that at that point there would be or it could be z minus a. I mean, that's not that important, but at the bottom it could be like z minus a over b. But the point is there would be a singularity at a. So the function would be undefined there. But if you look at the function we have here, e to the power of iz over z, well, that's defined everywhere besides at the origin here. The only singularity it has is at the origin, which is out of our contour. So the residues for this contour that we chose is 0. Which means that the integral I tilde is equal to 0. This obviously doesn't mean that the Dirichlet integral we're trying to find is 0, because they're not the same thing. But this is really powerful because we can relate the two, as we shall do now. So we will have I tilde explicitly, that's going to be, well, we're going to go from minus r to minus epsilon, right? That's this part. And then we're going to have the integral. But we're on the real number line right now. So that's just e to the power of ix over x dx, because z is x for that portion of the contour, plus. So now we're going to parameterize the semicircle now, but in a different manner, because we can't say z is x. We are doing a semicircle. And notice that we're going, well, how are we going? We're going from pi to 0, I think, or, well, we can say pi to 2 pi. It doesn't really matter, but let's say, yeah, from pi to 2 pi, right? If you just go around the contour, we're at a phased pi, and then we end up at a 2 pi. Or is that, no, that's not right, actually, sorry about that. That's from pi to 0, because, yeah, let me just think about this. So we're going clockwise, right? That's clockwise. So it should be pi to 0. Okay. And now z is going to be epsilon e to the power of I theta, because in this case that draws a circle centered at the origin with radius epsilon. That's what we want. So what is dz? Well, dz is I pi I epsilon e to the power of I theta d theta. So let's just substitute that then. We have e to the power of I epsilon e to the power of I theta. I'm just substituting for the integrand. Now for z, it's epsilon e to the power of I theta. Right? Okay, and then we have, what is dz? Well, dz is I epsilon e to the power of I theta d theta. Cool? That's the semicircle, the small semicircle. Then we're going to have, let's see. Then we're going to have from epsilon to r, again the same thing, e to the power of ix x dx, because z is x for that part, plus, I should move a bit. It isn't that different from the other semicircle. We're now starting from 0, going all the way up to pi, and the thing that will now, we will let z equal r e to the power of I theta. So we just get the result that we had, just changing epsilons to r's. R e to the power of I theta. And then, well, let's see. So that's going to be I r e to the power of I theta d theta. Now the trick that we want to do is we want to let, so I will say let epsilon go to 0 and r go to infinity. And the neat thing is, if you notice, this and this, well, they combine to give us, what do they give us? Let's see. So they combine to give us from minus infinity to 0 plus from 0 to infinity. That you can just call, so with those changes. And notice, this doesn't change the value of I tilde because the contour doesn't really change if you let epsilon and r go to infinity. That's still a contour that doesn't include any residues, any poles, as they call it. A pole is where there is a discontinuity, and then there might be an associated residue, right? That's the terminology. So we basically have that from minus infinity to infinity, e to the power of ix over x dx. Now we need to look at the semicircle integrals. So here you can see that these simplify, and then if epsilon is 0, then we have a 1 here, right? Because e to the power of 1 is e to the power 0 is 1, and then this integral then gives you, well, I d theta. That's going to give you an I theta as its integral, and then from 0 to pi, so that's a minus pi I. So I put a minus pi I there. Right. And now we want to also want to consider this integral. Again, these will simplify. And we're considering it as r goes to infinity, as we say right here. This one is a bit, well, it's a bit trickier than the other ideas maybe, but if you just consider this guy, right? That's, what is that? That's e to the power of I. You have the r here, if I can write that out, r. And then you're going to have cosine of theta plus I sine of theta. That's e to the power of I theta, right? And so if you now distribute, well, that's going to be equal to, let's see. So it's EIR cosine of theta. times e to the power of I times I is minus r sine of theta. And you have the detail at the end, right? What you need to realize is this part, e to the power of I something, that just oscillates, right? Because that's just a phase and it has magnitude 1. But this one, as r goes to infinity, you have a minus r here, which is minus infinity. So as r goes to infinity, sorry for the pencil, guys. It's not really working well. I realize that, but sorry for that. There's some disconnection. As r goes to infinity, this goes to 0, which kills the integral. So as r goes to infinity, this integral over the larger semicircle, the infinite semicircle, is 0. And this is a theme that occurs quite a lot in complex analysis. Oftentimes the path integrals along contours at infinity tend to be 0, but not always, but almost always, most of the time. But not always, as I said, you always need to check it. So this is it then, and this is equal to 0. Fine. So we have then that this is equal to pi I. Cool. But how does this help us? Well, what you need to realize is, if you consider the real part of this guy, right? What is the real part of the thing on the left side? Well, the limits will stay the same. Now this is the real part. And what is the real part of e to the power of ix? Well, that's just cosine of x over x dx. Well, that's 0 because that's also equal to the real part of the right, which is 0 because real part of pi I is 0. Now if you consider the imaginary part of the left-hand side, that's sine of x over x dx. And I can see that you realize where I'm going with this. This is equal to pi. Now, if you scroll upward, would you look at this thing here? We found that integral and we had said that I is just half of that. So then the Dirichlet integral, which was from 0 to infinity, sine of x over x dx, that's just pi over 2. And that's the answer. I also want to highlight sine of x over x is also called the sinc of x, the sinc function. So if someone asks you what's the integral of sinc of x from 0 to infinity, well, you know the answer. That talking about the Dirichlet integral, whose answer is pi over 2. And another common theme I want to point out in complex analysis is that we got this result for free. We didn't aim to compute cosine of x over x. We didn't want that integral, but we got it anyways. And this sometimes happens in complex analysis. So that's a theme, as I was saying. One thing you might realize if you're really careful is sine of x over x is defined at 0 because limit as x approaches 0, sine of x over x is 1. But this isn't defined there, right? There is a singularity at 0. And so what people sometimes put there is like I think they put like a principal value thing, like this is the principal value of this integral, and from what I know, what they mean is, you compute this integral ever so to the left of 0, so a minus there, plus ever so to the right, little bit to the right of 0, and then from infinity, dx, and that's equal to 0. They're not computing it at 0, but infinitely close to it. So if anyone was confused about that, I want to clarify that. To be fair, I wasn't confused about this when I first saw it. I realized there was a P at the front. I asked one of my friends, and then they explained that, and I also looked it up a bit at Wikipedia or somewhere. But anyways, this is the gist of it, and I hope you're just amazed about what we've done. Like, look at this. We found the integral of sine of x over x from 0 to infinity without doing any integrals. And sure, there were really some things you will need to think about, like this argument here. There is a more rigorous way of doing it, but I hope this explains the idea intuitively, and then well, this part obviously Cauchy's residue theorem. I didn't prove this, so you might have some questions in your mind. But as I was saying, I aimed this video to be an appetizer for complex analysis because it's such a beautiful topic. It's truly amazing. And it lets you compute these crazy integrals. Anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.